Hey everybody, welcome to this video where we will be solving the protein translation exercise in F#. We will do that via 4 different approaches, one of them being slightly non-idiomatic but performance related, and the other 3 are idiomatic ones. So what is this protein translation exercise about? Well, you get a string of letters, and that string is an RNA sequence. And RNA sequences are composed of things called codons. And codons are 3-letter segments. So let's look at this RNA sequence. There are 3 different codons in this sequence. So you have AUG, UUU, and UCU. So you can see that here. The next step is to translate these codons into proteins. So each codon translates to a single protein. For example, you can see that AUG translates to methionine, etc., etc. And one of the things to keep in mind is that different codons could have the same protein translation, and that there is such a thing as a stop codon. So either the sequence has been processed fully, and then you of course end up with the list of proteins corresponding to the codons, but it could also be that in the middle of the sequence there's a stop codon. So there are 3 stop codons, and if you reach that, you have to stop processing, and the proteins that are listed before the codon are included in the result, but after the codon, the stop codon, they are just discarded. So that's the basics of the protein translation exercise. Let's look at our starting point. We start out with a module with a single function, and that function is called proteins. It takes just a single parameter, which is the RNA sequence, which is the sequence of codons, and it returns a string list, which will be the translated proteins of the codons. So a string input, string list output. There is a set of tests. So we have tests, for example, that empty RNA sequences result in an empty list, and that individual codons can be translated to individual proteins, etc. And then there's, of course, checks that there's a stop. So translation stops if stop codon is at the beginning, etc., etc. So a lot of tests here. Let's verify that we haven't actually implemented any of these. Okay, that's good. So all our tests are failing, and we now have to build a working implementation. So let's do that in 4 different ways. The first approach that we will look at is a recursive one. We will define a helper function called doProteins, and we'll mark it with the rec keyword because we will be doing recursion. It will have 2 parameters. The first one being the unprocessed codons. So this is a string that will get shorter and shorter and shorter until we're done. And then there's a second parameter, which will get larger and larger as we go, because it contains all the translated proteins. So we will return the string list. And this proteins value is also known as an accumulator value because it accumulates the end result. The first thing that we need to do is we need to process these codons 3 letter at a time. So let's see, let codon be, so how do we get the codon? We could do several things actually. We could do codons.substring from 0 to, and have 3 characters length, which would be fine. But a more idiomatic F# way to do that would be to use slicing. And we're saying slice from index 0 up until and including index 2. So these are the first 3 characters. The next step that we take is we have to match these codons to proteins. So we can do that via pattern matching in F#. Match the codon with, and then we have to get all these individual codon values. So there was a list in the README. I'm just going to copy this list. I'm going to paste it here, and then I'm going to make this be actual F# code. So I have to add double quotes, of course. So let me start by doing that. Adding double quotes to all the string values. Here, and here, and here, and here, and here, and here, and here. And then do the same with all the proteins. Okay, and then we have a couple left. So, okay. Then this bar thing doesn't really work. We have to do a right arrow in F#. So everything after the right arrow is what's being returned. And we have to add, of course, the pipe signal before it. And we'll do that here too. So we almost have working F# code. The only thing that we don't have is this is currently trying to find a match of two values, so like a tuple, but we're matching on just a single string. But there's a very easy solution to this because F# supports having multiple patterns in the same row. So you can do this, just add a pattern, and we have to add it for this one too, which has 4 different codons all going towards the same protein. So what does this say? Well, it says we have to return a string list, and we're not doing that. And even worse, we're not doing any actual recursion. So let's solve that. So in case of we've matched the codon with awk, we will do proteins. So we're going to continue processing, but we have to skip the codon that we've just processed. So we're going to do codons 3 ... So this is everything starting at index 3. So we're skipping over the codon that we've processed. And then the second parameter is the proteins list. So what we will do is we're going to add this value to the list of proteins, which you do via the colon syntax. And this is now valid. So let's just quickly do the same thing for the other cases. And then we'll do this one. This is all a bit manual labor, but bear with me. Okay, so I like to align this for demonstration purposes because it shows the same structure being applied to all the patterns. So if we go to it, if we do a slightly horizontal scrolling, you can see that we're doing a recursive call in each of these cases. The new call's first parameter will have the first 3 values skipped, and then the proteins value will have the translated protein added to its list. So that's all preparing us well for the recursive aspect of the list. Our current implementation of the recursive algorithm doesn't really return anything yet, so let's fix that. So when are we done? There are basically 2 ways in which we can be done. Let's handle the first case, which is when we've actually processed all the codons in the string. So in that case, the slice will be empty, and we return the accumulated value protein. But there is one thing that we need to do. We have to reverse this. And this is because when we do these recursive calls, we prepend the value to the list. So it will be at the new first position of the accumulated value. And there's a simple reason for that, in that prepending to a list is a ton faster than appending to a list, which means that in the end, when we need to return the value, it will actually be in the wrong order. So it will be reversed. So this is a very common pattern that you see in functional programming, where accumulated values are accumulated in the reverse way around. So when you return them, you reverse them. So we handle that here by doing list.ref. And then finally, we have to call our helper function. So we'll call it with the codons. And initially, we will have the empty list. So we should have some tests passing now. Basically, all the tests that are not doing anything with the stop codon. So let's run our tests. And we got a lot of successful tests, and we see all the failing tests have something with stop in them. So, okay. So let's handle the stop codon. Let's go back to the README. Okay, these are all stop codons. So we're gonna have a separate thingy here. We're doing this again. So if it's this or that, then we reverse the list too. So we now have new cases where we stop our recursive algorithm, which are the stop codons. So let's run this. And it all passes. So we now have everything passing. The compiler is slightly unhappy though, because we have incomplete pattern matches. And that's because in theory, there could be an unknown codon. So it won't match any of the existing patterns. So what do we do then? I think the best way that we can deal with that is just by throwing an exception. We'll say unknown codon. Okay, this is all good. One thing that we can do is we can merge these three stop codons with this, but I'm okay with just appending that here, then doing like this, and that will be fine. So now we have all the stop conditions in the same place. We have our nice recursive algorithm that's very similar, and it all works. And this is also tail recursive, which means that for very large strings, this would work well. So you don't get a stack overflow or whatever, and it's performant. A final thing that I probably would do is I'd probably inline this value. So that's absolutely an option. And what you could do, you could consider it, is because this function is only there to help out with the implementation of the proteins function. We could move it within the proteins function. So we make it a nested function. And this now signifies to the reader that you don't ever call this function outside of the proteins function because, well, you can't. Whereas previously it might look like that. We could have made it private, but still. This is our recursive implementation of the protein translation problem. The second approach that we will look at is using the seq.unfold function. Seq.unfold is a function that implements basically the same type of logic that we just had manually implemented in the previous approach. So it is a recursive approach, but you can optionally stop the recursion before you're done with processing the entirety of the input. So how does it actually work? So let's look at seq.unfold and see its arguments. So there are two parameters. The first is a function. It takes a state and returns a t state tuple option. Quite a weird signature, but I'll explain it to you in a bit. The second parameter is simpler. It's the state. So in our case, that will be the codons. And the thing is that this generator function, the fact that it returns an option value is very important. So an option value can have one of two different states. Either it is sum with a value, which means that, okay, fine, we can continue our recursive execution, or it is none. And none signifies, hey, we should stop. So we will be using this feature to stop when we encounter one of these stop codons. So what is then the t state tuple? So the t value is the thing that gets returned once seq.unfold is done. So consider us processing the initial iteration of seq.unfold. The state will be the entire codon string, and we will take the first three letters and we translate it to its protein, and that protein string will be the t value. And then the state will be the new value used for the next iteration, which will be the codons except for the first three letters. So this is the way in which seq.unfold allows you to recursively go over an input and you decide which values to output. So let's just implement this and we'll see how that works. So let's see how we can implement that function that is the first parameter to seq.unfold. We could define it in line here, but instead for demonstration purposes, we'll not do that. We'll call a helper function called doUnfold. And that way we can be really explicit about the input and the output values. So it just gets a single parameter, which is the state. And in our case, the state is the remainder of the codon strings. And it returns the string tuple option value. So of course we have to pattern match on the codons. I have some code on my clipboard that does exactly the same thing that we did in our previous iteration, which is to match a codon's first three letters with explicit values and then matching it to its protein. but the type signature is wrong now because we have to return the string option type. The first value that is returned of the tuple is the value that is to be returned once Seq.unfold finishes. Okay, that's all good. That's all fine. But the second value we haven't yet passed in, and that's the new state. And the new state is what gets passed in the next iteration. So it's the remainder of the codons. So same logic here that we had previously. We'll just add it here. And then finally, we have to wrap it in an option value. So in this case, it's sum, because it's absolutely the case that we want the unfolding to continue happening. We're not yet done. So we do this, this, and this. And then our final step is to handle the stop cases. So let's start with the simple version first. So the empty string. So if we have the state be the empty string, then we're done processing. So we're telling Seq.unfold stop, and we do that by returning none. So the compiler is complaining because we're using Seq.unfold, whereas we are returning a list, but there's also list.unfold. So we'll just rerun our test and see if we have any passing tests. And we do. Basically, we have everything passing except for the stop codons. So let's just add those. I don't have it on my clipboard this time, but there are just 3 of them, so it's fine. Okay, and then rerun our tests. And we have everything passing. So just to be perfectly clear what happens, let's just go through it. Let's just consider the string AUG. So we're calling list.unfold, codons is AUG. So the first iteration will be codons is AUG, matching it with this case. We're saying, hey, return sum. The first value is this protein, and the remainder of the state is this. So what Seq.unfold will do, or list.unfold will do, is it will keep this somewhere in memory as the value to return at the end. It will call the same method again, but this time with codons 3. It will be the empty string. So that will match this case. List.unfold sees that none is returned, and then it will return everything that it ever got as the first value of a sum return value. In our case, it's just a list with 1 item, but you can see how that works for longer strings. And that's how you could do the Seq.unfold function. This is only really useful within the proteins function. So it's probably better to make it a nested function. Oh, sorry. And this should still work. The only thing that we haven't yet done is satisfy the compiler with the pattern matching. So we'll just do fill with unknown codon. And then we have the same working solution that we had previously, but using list.unfold. For our third approach, we will be exclusively using higher order functions from the Seq module. The only function that we will define is a function to translate a codon to a protein. So that's codon to protein. It takes in a single parameter, which is the codon string, and it returns the protein string. So what's different from the previous approach is that the codon will be a 3-letter string. So it won't be anything like the remainder. It's just the individual codon. I have some code copy pasted on my clipboard just for brevity. And we're matching the codons to the proteins and just returning the strings. This is fine. So we can already use this. We're not going to bother with the stop codon yet. So what we're going to do is we need to have some way of splitting up the string into 3-letter substrings. So there's a couple of ways in which we can do that. But one of them is using the fact that a string is actually a sequence of characters. So using sec.chunk by size. So we're saying this takes in 2 parameters. It's the chunk size, which is 3 in our case, and the codons. And this will return a sequence of 3 characters. So this is all very nice. We then have to convert the the sequence of characters into strings, because otherwise we will be matching on a char sequence, which would be not as convenient. So we're going to do sec.map. So this is our letters, and this is a char sequence, char array, I'd say. And we have to convert it to a string. So we're going to do system.string and then pass in the letters. So there is a function that takes characters. So this constructor takes a character array and returns a string. Okay, then the next step that we need to do is we have to translate all these codons to proteins. And we have a helper function for that. So we're going to say fun codon, and we say codon to protein. Pass in the codon. And then we're almost done. We have now a sequence of strings, so the proteins, but we have to convert it back to a list. So we're going to say sec.toList. And this should be our working implementation. So let's go over it step by step. Sec.chunk by size 3 codons means it splits the codon string into a sequence of character arrays. And each character array has 3 letters. So we then need to, as we want to pattern match on strings, we have to convert those character arrays into strings, which we do via sec.map, and then piping, calling the constructor, the system.string constructor with that letter, those letters. Then we have a sequence of strings, the codons, and we have to translate those codons to proteins, which we do via another sec.map call. And then we pass codon to protein. So we now have a sequence of strings, but those strings are actually the translated proteins. And we have to convert the sequence to a list, which we do via sec.list. So let's run this and see if we have anything that works. Okay, good. We have matching test, passing test, except for the stop sign, stop codons. Let's move on to the README. So what we're going to do is we're going to take the stop codons, and instead of doing something clever, we'll do something not as clever, I guess. We'll just return the stop string. So any stop codon will be translated to the string stop. So we can then use another Seq module function to stop processing when we encounter stop. And that function is sec.takeWhile. So we're saying, hey, this is the protein, and you have to continue while the protein is not stop. So we're adding an additional clause here. So we're saying keep on processing until the translated protein is equal to stop. So it won't include the actual stop protein, but it will stop before it gets to that. So now we have all tests are passing, and this is a very higher level way of looking at things. This is like a function pipeline. We could even do a little bit of refactoring. For example, this codons value, we could pipe it into. And this is a very F# way of looking at things, where you have a pipeline of transformations. We're already getting something that the IDE is warning us about, or maybe suggesting rather, that instead of having a function that just uses has a single parameter and then passes it to a function, you can simplify that to just this. This is the same thing, and I think we can even do that with system.string here, because constructors are also functions in F#. So this is our implementation using the higher level functions, just to have to compile and not complain about this unknown codon. That's fine. And now we have a collection of a sequence of sequence calls. Sorry. So chunking them first, converting the chunks to strings, converting those strings to proteins, and then continue processing them until we reach a stop sign. And if there isn't a stop sign, this will just return everything, and we're done. Our fourth and final approach is less idiomatic, but I wanted to include it anyway because it showcases some of the performance features that you can use on the .NET platform and in F#. So in one of the recent .NET releases, a type called span of t was introduced. And the idea of span of t is that it is optimal performance-wise. So you often have maybe an array or a string in memory, and you want to process that, but maybe you then want to process only a certain subslice of it. And as strings are immutable, you would normally create a copy of the string. If you do a substring, that will allocate a new string, and that is bad for performance. So what span instead allows you to do is to create like a view into the string. So the span itself is very small, and it will contain the starting point into the string or the array or whatever, and contain a length, so the number of elements that it will have the view over. And it's completely type safe, but the thing is that the span is allocated on a stack, and it doesn't allocate new values. It's just a different view. So you can work with spans on different types like strings and arrays, etc. And it is very memory optimal because it doesn't allocate much. And what it does, it allocates on the stack. So we're going to use that in this approach. As the implementation of this approach is almost identical in many regards to the recursive approach, what I'm going to do is going to swap this out with our recursive algorithm, which is almost unchanged except for the fact that I've moved the inner function to an outer function. So do proteins is now here. And let's see how we can convert this to be using span. So obviously we don't want to work with the string, but we want to work with the span. So how can we convert string to a span? So, there's nothing here that has to do with span, but there's a good reason for that, and that spans live in the system namespace. So we have to open the system namespace, and then if we do dot as span on the string, there is an extension method that we can now use, and it will return a read-only span of heart. And it's not a span of hearts, but it's a read-only span, and that makes sense because a string is immutable in .NET, so you can't actually mutate the string, so the span should also not be able to do that. So what you get is a read-only span of hearts. So we'll call that function method, and then we need to, of course, convert this into a read-only span of har, and then we are at a nice starting point, and then we have to deal with all these compiler errors. These compiler errors all have to do with slicing. And this is because a span and a read-only span are very low-level constructs. You can't do the fancy higher order things like slicing, etc. With the default notation. So we also can't do pattern matching on spans. So we have to do things a bit differently. So let's see if we can convert this awk translation to be working with the span. So instead of doing a slice, what we can do with a span is codons.startsWith, and we can pass in the string. So that does work. So we don't have pattern matching, but we do have a startsWith function, and that's absolutely fine for us. So what we then need to do, I'm just going to comment out everything just to make it slightly less obnoxious. So we then have to do a recursive call. So we're going to do the same thing that we did before. This still works, the prepending to the proteins list. It's just that this slicing thingy doesn't really work. But there's actually a method, and it's called slice. And this is sort of like the crux of the read-only span approach, because what this does, it doesn't allocate a new string. It just changes the view to ignore the first three. So you could almost see it like the left part of it is sliding right 3 steps. So it will allocate a new span, but the spans are cheap. So that's all fine. The compiler is complaining because we have to have an else branch too. And we'll just use the fill with thing. So this is all fine. Now we have a span based approach to dealing with the codons via the starts with method and using slice for the next thing. We can't yet, we could run this, but it wouldn't really work because we have to detect when we are at the end. So I'm going to add as I use it as the first condition, if codons dot is empty. So there's a built-in property that we can use. Then we need to do the list.ref of the proteins. Else if, okay. So we're just focusing on the aug protein right now. So we're saying if it starts with aug, then we continue, but we change the span to ignore the first three, and we stop when it's empty. So that's all good. So let's try and run some tests and see if we get anything that passes. And we get 2 passing tests. So we have our basic setup actually working for the aug codon. And let's do some magic to just convert the existing match code to the new structure. So I have on my clipboard a lot of code that replaces this with our new structure. So there's a lot of repetition now. So this is arguably one of the biggest differences because we can't do pattern matching. So we have to have a starts with clause for every single one of these individual codons, even when they have the same value. So we could do or, etc. But for now, we've just done it like this. We have the codons empty case, which is reversing the list. And we also did the same thing with the stop codons. And we do the same reversing of the list. So obviously we could reduce the amount of duplication by doing ORs, but it would still be fairly, it would be a much bigger bit of code than it is for the pattern matchings. So let's run this code. And we now have everything passing. So you might wonder, what did we actually gain? So we didn't gain anything regarding to readability because this is arguably a lot less readable. Although starts with isn't that bad, slice isn't, but it's very verbose. But the thing that we gained, if the codons string is very big, then our previous approach would create a new substring for every iteration. So whereas instead this span-based approach is so much more faster because it doesn't allocate new strings, it just allocates spans. And if you are interested in the performance results, we have on the website an article on comparing the performance of the various approaches, but this is by far the fastest one, and it's mostly due to the fact that it doesn't allocate new strings. So less allocation is a good thing. This is not something that you would write by default. You would only be writing this code if you think the code is on a hot path where it really influences the performance of your implementation. And then you could write it like this. It's more low level, but it has its purposes and it is a lot faster than the other approaches.